Oh, that's the last one of the forms I put at the end. Right? Where I said the line integral of x, blah, blah, blah. It's one of those formulas. It's a plug and chug. Really didn't think of that. Forgot it. It's just one of the applications. I don't really care about that.
So no, it won't be a test?
Huh? No.
Okay.
But it's one of those forms. They're one of three formulas that you just, you know, if you applied Green's theorem, you get the double integral, so you just do that line integral and you get the areas. So, 13. Anyone has the question? F is equal to x plus
Oh, that one? Yeah.
Huh?
That one's just tricky. But easy enough.
Tricky.
Yeah, kind of, because you have to use double angle theorem.
The what?
No, sorry, not double angle theorem, but you have to find the integral of sine cube. So just, yeah.
Well,
Anyway, it's easy, but still.
but,
Yeah, exactly.
yeah, so the idea is this was back in 13.2 when I actually spoke about this, and I said that, well, if you parameterize by the canonical parameterization r equals xy, you're supplying a point, then that means your dr would be dx dy. And if your f is equal to pq, then your f dot dr is just equivalent to this guy. Right? So in other words, this is just like the Green's theorem formula, except I know that this is the p and this is the q.
Yeah, I did say exactly.
Right? And so we are going to want to, so p is equal to right by x plus y cubed, q is equal to x squared plus right y.
I think
So
there's a minus, no? A minus q.
Yeah, it's minus, well, using the...
Not plus, it's minus.
No,
what do you mean? No, that's right.
no, it's not. Yeah, it is.
It's a funny formula,
Yeah, that's yeah.
P with respect to y is 3y squared, q with respect to x is 2x. So we know that the integral on f dot dr is equal to the integral of p dx plus q dy is equal to the double integral over d of qx minus py to a. And in this case, we're going to have a negative because we're moving counterclockwise. Clockwise. Right? Because look at the formula. That's the picture. So the sine looks like this. It's pi here. You're moving along that. Y equals sine. And you're coming back along this guy back to 0. So you have a closed curve, so Green theorem applies, but you're going you're going clockwise, so it's negative orientation, so you have to put a negative in front of the double integral. And so we'll get the double integral over d of 2x minus 3y squared. Which you can set this up. If I let x go between constants, x would go between 0 and pi. Let y go between functions, it will go between 0 and sine x. And so you just have to do that integral, right? So integrate with respect to y, I split this up. Right, this you have to do integration by parts. Right, so it's the integral of this times that minus the integral of the same thing times the derivative of that. It will be 2 minus. Here, the sine squared, you think of 1 minus cosine squared. Do a u substitution. So this is really 1 minus u squared du. This would be a plus because derivative of cosine is negative sine, so you factor the negative out, makes this plus. Alright, so this is going to go to 0. Here, plug in pi, you get minus 2 pi. Cosine of pi is what? Negative 1 makes this positive. And cosine of pi here is negative 1. Minus cosine of pi here is negative 1. You cube it. You get negative 1. Take the negative, you get positive 1. Minus, open brackets, that would be 0. This would be 1 minus 1/3. Sorry, this was a 1/3. I think I forgot a negative. Minus 2 plus 2/3. So this is 6 over 3 plus 2 over 3 is minus 4 over 3. To the negative, you get 4 over 3 minus 2 pi. And that means. Okay. So the trick is following. To realize that f dot dr, you could write it so like something like this. And this is the formula from Green's theorem. And so you know that the p and the q are just the components of the vector field. Right? So this was the p, that was the q, so now you just find the partials, plug into the formula. Be careful because of the negative orientation, so you have to have that negative sign here, and then after that it's top 2. Right? Any questions?
How do you get still the sine x?
Oh, that's how you set up double integrals. Remember the last integral goes over constants, right? And that was with the x. The inner integral goes between functions, and that matches with the y. So here, x goes from the left constant to the right constant, that's 0 to pi. Y would go from the bottom function to the top function. So the bottom function is y equals 0, the top function is y equals sine x. So that's the setup.
So it's negative because it's going clockwise?
Because it's clockwise, right? So remember Green's theorem, it had in the theorem that this is for positively oriented curves. Positively oriented means you're going counterclockwise. If you're going the other way, all you have to do to change that is just to put a negative in front.
Positive orientation, negative orientation is by definition. It's not really anything special.
It's by convention, yeah.
Okay.
It's sort of like how, you know, in physics, velocity, you say upward is the positive direction, downward is the negative direction.
Okay.
Just because.
When you're doing it directly, does the same convention follow? Clockwise is negative? How would you do it?
If you were doing it directly, the way you set it up, it would have the parameterization built in, sort of. Like for example, if you're making the line segment from this, the way you'd set it up, it would automatically start here and end here, right? Based on if you do that initial final formula. So the direction is sort of built into your parameterization. So you have to be careful, you wouldn't really need a sign. But if you just ignored the fact that it was negatively oriented and did everything, and then at the end you just say, it's the negative of this because it was negatively oriented, then you'd still get the right answer. Any other questions?
So you're not going to be 19?
No. Okay. Okay, so last time before the test, we did Green's theorem, which was a theorem that says, well, if C was a piecewise smooth curve on an open connected set, then the following is true. If C is positively oriented, blah, 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 right? Integral P dx plus Q dy equals the double integral over D of Qx minus P.
Question.
Yes?
Green's theorem, its job is to only make our life easier. It's not really.
Yeah.
Yeah, that's it. Just
Yeah.
make life easier. Okay. So
Right.
any problem can be done directly or with Green's theorem.
Any problem under these conditions. So remember, the thing with Green's theorem is, one, you're in 2 dimensions, right? So you only have 2 variables to work with. And secondly, you have a closed curve that's piecewise smooth, right? So in those conditions, you can apply Green's theorem. Doing a line integral around the boundary of the region is the same as doing this double integral over the region itself, right? So Green's theorem really relates a line integral around the boundary to a double integral, a scalar integral over the region, right? And like we said, this guy is actually equivalent to f dot dr if f is pq and you take r to be just parameterized by the coordinates themselves, x, y, right? Right? So this is Green's theorem, works in 2 dimensions, piecewise smooth closed curves, right? If you do not have any of these conditions, you cannot apply Green's theorem. Okay. But that was Green's theorem. So this is one of the 3 major theorems, like I said, that we'll be doing in vector calculus. The other 2 we'll be doing is Stokes' theorem and Divergence theorem. And they basically have the same sort of setup. They're going to relate a line or surface integral around the boundary of something to a scalar integral on the region itself, right? And they're going to be doing it in higher dimensions. Green's theorem is the 2-dimensional.
Generally,
version.
will a question tell us which theorem we should use or no?
Of the past finals on the math website, all but one always tell you that you have to use
So,
that
it's,
theorem.
so you know immediately what kind of method you should have, right?
Yeah.
Yeah.
But you should know the conditions. So Green's theorem, closed curve, you can positively oriented, only 2 dimensions, you can use Green's theorem. Right? So these are things you should use. Okay? And they sometimes make your life easier because sometimes this guy can be a real pain to compute, especially if your C has many parts to it. You have like 4 curves creating this thing. You don't want to do 4 of these integrals, right? It's going to be easier to do just 1 of these integrals, right? So it does cut down on your work somewhat, right? So that was Green's theorem. And like I said, our goals are to do Green's theorem, Stokes' theorem, Divergence theorem. And for Divergence theorem and Stokes' theorem, we actually need more machinery, so that's what we're going to be moving on to now. We're going to need to know about the curl and divergence. Okay, so Stokes' theorem is going to use a guy we call the curl. Divergence theorem is going to use this thing we call divergence. Right? And so, let's begin. First, we're going to introduce a convention, del operator, and we're going to use it to define these operations on vector sheets.
It's the same thing as the gradient.
Come again?
It's not the same thing as the gradient.
No, it's not. It's similar. It was inspired by the gradient. Or by a way to do this. So there's this operator that in 2D it looks like this, in 3D it looks like this, and it's just like a vector with just partial derivatives, but they're not attached to any functions. So it's just a convention. By itself it means nothing. It's like you have ddx floating around. It doesn't really mean anything unless you say ddx of something, right? So on its own this thing means nothing, it's meaningless, but when you attach it to stuff it has meaning. For example, as he mentioned before, gradient is an example. example, when you say the gradient of f, you could think of this as, let's say f is a two-variable function, right? You could sort of think of this as d dx, d dy times f, right? Which, you know how to multiply vectors by scalars. You just multiply each component. Right? And so this notation, if you think of this as just a differential operator, it makes sense in that regard. Right? So that's an example of, it means something when it's attached to something. It's an operator. It has to operate on something. Right? And so that's the del operator. Okay? You might see it referred to as the del operator. Or something similar to it. Okay, so that's del. Now we're going to define the curl.
Del has supposed to have two L's, isn't it?
No. Let f be a vector field, P, Q, R. The fact that it's 3D is going to be important, as we're going to see in a short while. So here's the curl. This is the guy we're going to call the curl. It's a particular kind of vector field.
Is there a shorthand?
That's the curl.
Is there a shorthand for the curl?
Yeah, there is.
I mean, running curl seems a bit long.
Yeah. Because we are going to, of course, you're going to have that memorized finally. So. Of course, there are always, conventions that help us memorize things. So memorizing that guy is a daunting task. It's really complicated. But you should notice that curl f is actually equal to the del operator cross with f. Right? So this is why 3D was important. Curl is only defined for 3D because we only define cross vectors for three-dimensional vector fields.
Okay, so instead of the word curl, we can just write del cross f.
No, well, you never actually write this down, but this is how you're going to think of it. So, for example, f equals p to r. I'm going to show you how this general formula comes. Then the curl of f would be equal to del cross f, which, as you might remember from calculus 3, that I, J, K is the determinant of this matrix. Right? Now how are we going to find the determinant for this guy? How do you find the first component?
Well, cover I and then multiply.
Right, you cover the I column and you
Yeah.
cross multiply it.
Yeah.
This times this minus that times that.
And you
So it's
just,
partial r with respect to y minus partial q with respect to z. The
then
second
J's-
component you always put a negative,
yeah, J's negative.
right? You cover up the middle component and you do the same thing. This times this minus this times that. So it's partial of r with respect to x minus partial of p with respect to z. The final component, you cover up the final guy. This times this minus this times that. Partial of q with respect to x minus partial of p with respect to y.
Professor, it wouldn't matter if you went the other way around, like you did partial of r with respect to y, I mean partial of q with respect to z minus partial of r with respect to y,
Yes, it wouldn't be correct. It wouldn't be the same.
but it just be negative for whole thing.
No, that's how it's defined. This is the determinant.
Okay, so we have to go left to right, okay.
Yep. Okay. So that's how you figure out the curl of something. Okay, so yes.
Would you say that Green's theorem is like a special part of curl, just the last one?
Yeah, you might notice that this guy here is the guy in Green's theorem, but there is a connection, and we're going to do it. Because we use this guy in Stokes' theorem, and Stokes' theorem is sort of like a higher dimension of Green's theorem, so they're really sort of connected on some level. But yeah, there is some connection. It's not one we're going to explore, but there is something there. But yeah, so that's the curl of a vector field. Let's actually do an example. I want to find the curl of that guy.
So there really is no quick way to write curl, there's no like C or that?
No.
Okay.
No, that's how you write curl. That's it.
Okay.
That's notation. Okay, let's begin. So curl of f. Remember, we're just going to take it to be I, A, K of partial with respect to x, partial with respect to y, partial with respect to z of x y z,
X,
x y, q y q. So in the first component, what are we going to have?
6y squared.
Partial with respect to y of this, right? So it's going to give me 6y squared minus 0, right? Because partial with respect to this guy, these guys are constants with respect to z, so right? The middle term, you cover this guy up. Partial with respect to x of this, which is 0, minus partial with respect to z of that, which is xy. Right? So it's minus xy, but you automatically just take the negative of the middle component and get that guy. Cover the last thing. Partial with respect to x of this guy, 2xy. Minus partial with respect to y of that guy.
So this is also like, with the cross product, is it perpendicular to this vector?
No, well, del is not
Yeah,
really a
nothing.
vector. It's not really anything.
Like that,
It's,
or that vector,
You
does it describe like
What is it?
it does describe something. I'm going to talk about that later, actually. But it's not anything to do with directional.
The thing is, why does it work? Why does I mean, if del's not a vector, why does it the cross product work?
Oh, this is just a nice mnemonic word.
Ah, okay, so
I mean,
they don't yeah.
the real deal goes back to something called wedge products. The curl F is a very is a specialized case of a wedge product, which you're going to have to like study some really high math to figure that out.
Wait, so
Yeah.
that is a vector then?
This is a vector field.
Oh, yeah,
Yes,
that
and
is
it
vector.
does give us certain information, but not necessarily in terms of the direction of this guy. We're going to talk about the meaning of this vector field later on, and of course the name curl is very suggestive.
Rotation.
And it's talking about rotation and stuff like that. Yeah, we'll talk about that a bit later. But the curl is just another vector field, and its relationship to this vector field is talking about something about how it rotates and how it curls around something. Right? But yeah, that's how you compute it. You take that determinant. Okay. Any questions? Yes.
For the vector field, will it always be in the order of P, Q, R?
Yeah. Yeah.
Because I know in the green stuff it says they can rotate them inside and compute.
Oh, that's when it's in the scalar form, right? They can put the dy first and just to trick you, but yeah, this is just our convention. We just call the first component P, the second component Q, the third component R. You know, it's just names. Here's a neat theorem.
Conti second?
Come again?
Conti-
Continuous. It's short for continuous. There's a theorem that says the curl of a gradient field is 0. It's actually not difficult to prove. It's a very computational thing. You know that the gradient of f would just be fx, fy, fz, right? So if you take the curl of the gradient of f, you would just get I, j, k, partially with respect to x, partially with respect to y, partially with respect to z, of fx, fy, fz. Now if you do this guy, you would get, this guy would be f of z y minus f of y z, comma. The middle one would be f of z x minus f of x z. The last one would be
f of yx.
f of yx minus f of xy. You might remember a theorem from Talk 3 called Clairaut's theorem.
Clairaut's what? Oh yeah, yeah. We don't call it Clairaut's.
That if you have f of xy, it's equal to f of yx, etc. Right? So these guys are actually the same thing. And so you end up with the curl of the gradient is actually equal to 0, 0, 0, which is the 0 vector, right? So f of zy is equal to f of yz, f of zx is equal to f of xz, etc. You can switch the order of partials once your function is continuous. That's by Clairaut's theorem. That we
So it's basically conservative then.
well, yeah, gradient field by definition.
Yeah,
are conservative.
yeah.
Yeah.
Wait, so is that like analogous to the fact that when you have determinants, if you factor out a common factor and two rows are the same, like there's a 0, the determinant is equal to 0, like
What would be a common factor here?
because like I mean it's not really a common factor because that was an operator. It's not an actual like multiplicative thing.
Yeah,
If you thought of the f like as a common factor, you'd see that the there are two similar rows, and like when you generally have determinants, if you have two same rows, it's supposed to be 0.
if you have one row as a multiple of another, yes, but in this case it's not. that's not what's going on.
So that's not analogous, there's no
No.
analogy to that.
No, there's no analogy to that.
Okay, so the reason
But
why.
we do know that the curl of gradient field is 0.
So it's like so it's gonna be some sort of loop or a circle-ish thing.
No, means there's no curl.
Okay.
But if you have a vector field equals the gradient of function, then what can you tell me about the vector field? That it's conservative. Right? This means what? If f is conservative,
Integral around is closed band is 0.
then the curl of f is going to give me 0. Right? It will always give me 0 if f is conservative.
Okay.
Right?
So if the curl is 0, then we can say that f is conservative. Wow.
From this statement, you can't make that conclusion, but the converse, which is the statement you want to make, is true if f is continuous on R3, right?
Oh, okay.
And that's, technically you only need like an open simply connected set and then it's conservative on that set, but we're going to give you stuff that's continuous everywhere, right? So that is, in this case, curl f equals 0 implies that f is conservative. So remember back when we had two-dimensional vector fields and we wanted to check if it was conservative or not, we just did that little equation, right? Check if the partial of p with respect to y was equal to the partial of q with respect to x. It turns out that this is the test if you have a three-dimensional vector.
Three-dimensional.
Is the curl the 0 vector? If it is, and all your components are continuous, then yes, it's conservative. This would be your check. So as you can see, just going from 2 dimensions to 3 dimensions, the check becomes a lot more complicated. You don't want to see the 4-dimensional check.
What?
Okay, so with the curl, we've developed a way to actually check if a 3-dimensional vector field is a conservative vector field. And of course, that's going to have all sorts of neat consequences. So with this, we can start to consolidate a lot of concepts that have been floating around. We're actually going to start tying them together and unifying some things. So here's a theorem that says the following are equivalent. So equivalent means they'll all happen at the same time, or none of them will happen at the same time. Right? Suppose we're going to have to, f is a vector field with continuous So if you have a 2-dimensional vector field whose components has continuous partial derivatives in R2 or R3, should put that out first. Then the following are equivalent. 1, f is conservative. 2, the integral f dot dr is independent of path.
What do you mean by equivalent?
They will both happen, they'll all happen at the same time, or none of them will happen at the same time.
Oh, okay.
Which means if you know it's conservative, it automatically means this is independent of path. If you know this is independent of path, it automatically means the vector field is conservative. Right? They'll all be true at the same time, or they'll all be false at the same time. That's what equivalent means. 3. F dot dr equals 0 for any piecewise smooth closed curve C. So if I know it's conservative, it automatically means this vector is independent of path. This automatically means that this is 0. And this one automatically means the other two. This one automatically means the other two. Once you have one of them, you have all of them. Right? 4. Parts A and B. Partial of P with respect to y equals the partial of Q with respect to x. If you know your f is, looks like PQ. B. The curl of f will be equal to 0 if your f is 3-dimensional. And that is the theorem. Right? So that's to say the following are equivalent. If you know any one, you know all the others. Right? So if you know it's independent of path, you know that this is true, that's true, that's true, that's true. They'll all be true at the same time, or they'll all be false at the same time. Right? So if you don't have any one of these, you don't have any of the other ones. Right? If you have any one of these, you have all the other ones. Right? So that's going to help you to solve problems, right? So if you know that in a word problem they say, oh, you know, f is conservative, it automatically means that all these things are true, right? So you can use any one of these to your advantage that you'd like.
Question. Is potential function strictly any function that that will have a gradient of f?
Yeah, any function that you
Will have a gradient of f.
Yes.
So it's a scalar gradient. So it's strictly gradient.
Yeah. So this definition, if curl f equals, this is just some vocabulary, 0 at some point, then f is said to be at that point, right? So they say something's irrotational, they just mean the curl is 0.
Is that possible? Can object be irrotational here?
Yeah. I'm going to give you some examples later. I don't know if I'm going to get to today, but yeah. They definitely do exist. For example, any conservative vector field will be irrotational. So you know at least there's one class of functions that will work. So that's all I have to do with the curl. Let's talk about divergence. And we're going to revisit both of these to talk about what they mean, you know, as the physical interpretation of them. But yeah, we'll talk about divergence. The last one was the cross product, this one is the dot product. So in particular, if f is equal to pq, then the divergence of f is just partial of p with respect to x plus partial of p with respect to. So let's do the same trick like you would if you were finding the gradient of this guy, except it's not a vector, it's a scalar. Plus and
Does divergence relate at all to the divergence series or not?
no, it's not a series.
No, no,
Both of these guys are describing vector fields. That's what the curl and divergence over there.
okay.
They're not describing series.
No, but divergence from series, something like
It's talking about like if your vector field is diverging from a point
Oh, I
or
see.
not diverging, right? That's sort of the interpretation of that point. Let's see. Example. We're going to go back to the same function, x, y, z, x squared y, 2y. Find the divergence of that. What's it going to be equal? Oh, I can write it out. The partial with respect to x of x, y, z, plus the partial with respect to y of x squared y, plus the partial with respect to z of t cubed. So this is what? Plus 0. That is the divergence of this thing.
Can't you check the gradient? I mean,
Yeah.
never mind, never mind.
It's not a gradient, it's a scalar.
I know,
Right?
yeah.
Divergence is a scalar, the curl is a vector. Here's a theorem. we're always assuming nice things like continuous. Second round of partials, then following is true. Divergence of the curl is 0. If you take the divergence of a curl, you always get 0. Proof. Let's do the reader. So again, it's very computational. You just take the formula that you know for the curl, you plug it in here, find the partials of each component, add them together. They'll all die. They'll all cancel out, so you just get 0.
Oh yeah.
So it's very computational. Plug and chug, and you'll see.
So it's for every curl, not just conservative curls.
No, any curl. Right?
Okay.
Curl. The divergence of a curl is
Any
always
curl,
0.
okay.
So I mean, like, I guess I'm thinking about when you learned the dot product of A dot A cross B. We learned that that was equal to 0 because like there was something
The
like,
dot product of what?
A dot A cross B, the vector A cross B, A dot A cross B.
Yeah.
Like, is there any analogy again? Because
Uh,
del dot del cross F is equal to something like that.
No analogy. I mean, that's just a direct consequence of the fact that A cross B is actually orthogonal to A. So if you take the dot product, if you take the dot product of two orthogonal things, you get 0. It's,
So
Yeah,
there's not like
no, not really. This is just a neat little thing that you notice. This, for example, you can prove that not every vector field is a curl. Just like you know not every vector field is a gradient field. You can prove using this that not every vector field is a curl, for example. Show that this vector field, G, x1 squared, squared is not
So using this logic, we'll be able to figure out the function that has a curl. Like you might give us a curl function, and then we go backwards to find. Like eventually, we'll be able to.
This is just a way to recognize when something is not the curl.
Yeah, but why would we need that? That's the whole question.
Technically, we're never really going to use that, but there are a lot of homework problems. It's good practice too. They're homework problems. Besides, it's a neat thing because I mean, some people ask me all the time, how do you know if everything's a gradient function? Not everything's a gradient function, right?
Well,
You can prove that, and here we're going to prove that not everything is a curl function. In particular, the curl is used in a lot of places, in particular in Stokes' theorem, so you're going to want to know when you can apply things like that. So, assume to the contrary it is a curl. Then you take the divergence of the curl of F. It's the same as taking the divergence of G, but that would just be y squared plus z squared plus x squared, which is of course not 0. Contradiction. Therefore, G is not a curl. And it's always good to know that definitions aren't redundant or random. Right? So a lot of times if you're learning about something, you're going to want to be able to pick examples and non-examples of these things, right? Because, for example, if everything was a curl, there would be no reason for the definition rule. But this is proving that the definition does have a point because not everything is a curl, and the curl is actually useful. Another definition. If the divergence is 0, then f is said to be incompressible. And again, these are very suggestive of the physical properties of these vector fields. So if curl is 0, you're irrotational. If the divergence is 0, you're incompressible.
So I'm guessing spring. So I'm guessing like a spring.
A spring?
Yeah, because the spring can both be compressed and
Like
displaced.
the expansion of a volume element, like you can have fluid, you have a
Water.
volume element, like
Yeah,
you can see it go
I
out.
mean, we are talking about things with vector fields here. I mean, how would you model a spring by a vector field?
Some wave kind of.
All right, so it could mean fluids,
Waves.
electric fields, wind, right? Anything that you can model by a vector field, anything that fills space
Well,
and
you
flows
can draw
somewhere.
it. in a vector
The volume
field.
element doesn't expand, it's like, the divergence models out,
Some light
maybe. The divergence.
waves.
Anyway, so yeah, that's it. That's all I need to know about divergence. But now let's talk about what they all mean. Interpretation. So I'm going to illustrate using some examples. So consider the following illustration. Curl. The example. Alright, so technically curl is in 3D, but I'm going to just take a 2D dimensional image, right? Pretend that the z-axis is actually sticking off out of the board. We're just going to be having a bird's eye view of what's going on with this thing. Alright, so take our vector field to be x, y, 0, right? Just kill the z coordinate, and we're just looking at what's going on with this vector field in the x, y plane. This is actually a vector field we've drawn before. When I was doing 13.1, I actually spoke about this particular vector field. You remember what it looked like?
Yeah, that's
They were like, its skeletons were circles. And you had the arrows pointing out
yeah.
in all directions. Right? The farther away you get, the more the arrows stretch out.
There's a name for that. I forget.
Right? So that's an example of what that vector field would look like. Right? Now let's see what the curl actually tells us about this guy. What do you think the curl would be? If you had to hazard a guess. Positive value, a negative value?
It's conservative to me.
Positive.
Right? Like pick any point. Is there a rotation going on around this point?
No.
Is there a rotation going on this point? Or that point? Or that point? Or that point? nothing's rotating. We'd expect the curl to be 0.
So it's conservative, basically. Okay.
Curl F would be the I, J, K of partially with respect to x, partially with respect to y, partially with respect to z of x, y, 0. So that would be 0, 0. This would be 0, 0.
You seem bored.
This would be 0, 0. Get bored with the computational things, you know? So 0, right? Right? Because there's no rotation. Right? In other words, there's no curl. There's no curling going on. Right? So this vector field doesn't have a curl. It's the same as saying there's no rotation going on here. Right? In this fluid field or vector field, wind field, liquid field, there's no rotation, right? Nothing's going to be spinning around any one point in this vector field. And I can tell that. I don't have to draw the vector field to know that. I can just take the curl and know that.
Professor, it's possible to have some vectors on your actual vector field curl? I mean, actually rotate, but have others in the vector field that don't rotate?
Yeah, and non-conservative vector fields do that.
Okay, so in that case, we would have a value for it.
Yeah, you'd get a value.
But how do we tell the difference between some vector that does curl, that does curve, and
I'm going to give you an example
Okay.
of something like that later, right? But this is an example of something where the curl is 0, and this
All
is
of them.
really what's going on, right? It just means there's no rotation, there's no curling around any point going on in our vector field. Now take F to be this vector field. Y minus x common 0. If you compute the curl of this guy, you'd actually get, just skipping the word, 0, 0 minus 2. Right? So this is a non-zero vector for the curl. What's going on, right? Well, we can draw a picture of this guy.
Yeah, it spins.
Now you might remember this guy. This is the guy that I said would be a fairly good model for
Whirlpool?
a whirlpool, water going down a drain or something. Right? Now, how do we interpret this fact? The curl is actually a -2 in the z component.
Vector field rotate toward the z.
It means that if you're looking in 3 space, for example, right? If I extend this guy to 3 space, what would be happening? The guys would be pointing down at the same time they're swirling around. So it's actually a pretty good model for water going down a drain. Your z component is negative, you're moving down, right? So I'm swirling around the origin at the same time I'm moving down, right? So this vector field is actually a good model for, or a very rudimentary model for something like fluid flowing down
How
the
do you find
drain.
that out?
And I could tell that from the curl, right? I do the curl of this thing and we're like, okay, so there's a lot of swirling going on, and it's sort of swirling around the origin, x and y are 0, my z component is negative, so things are going down while they're swirling. So I can tell all that just by finding the curl of something.
So is there like a clockwise, counterclockwise association with curl, and it being negative or positive?
Yes. Well, in this case, it wouldn't make a difference because the z component is negative. But yeah, if I put a negative here and a positive here, it would go the other way. But
So it's
there's
like
no.
it's rotating around the z on the plane of the xy, the rotations.
Rotating around what?
Z
Like
axis.
an axis.
The axis?
The,
Yeah, it's rotating around the z-axis. But there's no real like counterclockwise or clockwise distinction. It's just what you have.
So the larger negative the number, the
Yeah,
steeper.
the faster it goes
Yeah.
down. Right, so. Right, so yeah, water going down a drain. That's the equation. Okay, so here, what's this one? them here have rotations. So these objects aren't the curl and divergence. They're not just random things that mathematicians just like, oh, look at this trick. If you do this determinant, no, they actually tell you information about the vector field you're studying. And you can use computations and you can describe a vector field that otherwise might be very complicated to graph, for example. Or you can know things about your vector field just by the information given by these two operations, del cross f and del dot f. So it's just one way in which derivatives gives us another interpretation of our world, right? So in Calc 1, you take the derivative, you interpret that as rate of change, how fast something is. Well, in vector fields, if you take these partial derivatives of the components in this particular way, you can interpret it to mean how your vector field is curling or how it's diverging from a point, right? And speaking of diverging from a point, let's actually find the divergence of both of these vector fields. Hopefully at this point you're starting to see some indication of how you use this in physics and engineering and stuff like that. How you can use this to analyze anything you can model by a vector field, which is a lot, right? Electricity, and a lot of things you can model by vector fields. And these are really powerful tools.
So this vector field here means that the change z is kind of constant?
Yeah, at any level, it's moving down at the same rate. It's negative 2. You can think of it that way. If this was a function, it means depending on the level you're at, you might be going down faster or slower. Yeah. But here it's constant, so everyone's going down at the same rate no matter what height you're at.
How did they figure out that? Like, how did we find this out anyway? Like, how did they find out that you could represent like a whirlpool like that?
Well, in 13.1, I actually drew this for you in 13.1.
So they just graphed it.
So someone was graphing it and like, oh, that's interesting, it's a swirl. And then they tried to, I don't know where they get this stuff from. You ask myself the same question a lot of times in my own math class. What? Where? How? What? Okay. Yeah. So now. In graduate classes, it's even crazy, trust me. You've got like this huge thing like summations and integrals and double integrals and this and that going on. You're like, oh, this gives you that. Like, what? How do you? Okay, if you say so. And then they're like, oh, here's a proof. Okay, fine, I see the proof, but how do you come up with that? Yeah, I don't really know, but I just know that this works. Yeah, so back to x, y, 0. Oh, they're already here. All right, so we're looking at this vector field again, and what do you notice? Look at any region, right? Like, pick a region in here, like in this box. Right? What do you notice about divergence within this region? Well, things that are entering, they're entering pretty slowly. But things that are leaving pretty quickly. Right? There's divergence going on in this region, right? Things are coming in slowly, but they're rushing out, right? So things are diverging within this region. And it's going to happen basically to any region you pick.
Things are going further away from it.
So, for example, here, you're not going to expect the divergence to be 0. You're going to expect something to be going on.
There's also have a value for the curl and the divergence.
Yeah. So their values are interpreted in, So here, if you look at that divergence of f, that's just the partial with respect to x plus the partial with respect to y. That's 2, right? Notice that it's positive. This means if you pick some region vectors which really represent anything, fluid, electricity, current, vectors enter vectors leaving greater magnitude. We call this positive divergence. So this vector field, as you can see, if you take a snapshot of any one region, you have a lot of divergence going on. Things are coming in slowly, but they're rushing out quickly, right? And if it was the other way around, you have long vectors entering, small vectors leaving, then your divergence would actually give you a negative value.
So that would be a negative divergence.
We're going to look at this one first. Yeah, so let's start with this one. We're going to reinterpret this in terms of divergence. What's the divergence here? Partial of this with respect to x plus partial of that with respect to y. 0. There's no divergence. The trick here is if you pick any one region, right? Remember these guys are like running along circles, right? On any given circles, all the vectors have the same length, right? So vectors entering along any one of these paths are the same as lengths as those leaving. So there's no divergence, right? Within any region we pick, there's no change, nothing is rushing out, right? They're pretty much, everything is just like static, sort of, right? That's what I say. It's incompressible. You can't really speed anything up or slow anything down. Everything is just moving together. And so we end here. So
Wait, for all specific circles? For any
yeah,
specific-
yeah.
What, wait, for that graph or for any graph?
For this particular
Okay,
one.
okay.
Right? So we introduce the curl and divergence, and these are their physical interpretations, and later on we're going to actually use them in theorems. There's going to be something called Stokes theorems, where we're going to relate line integrals on boundaries to scalar integrals on regions, and it's going to use curl and divergence, and we're going to come back to all this.
When you think the next time we're like,
Quiz Monday, I guess.
This Monday?
I did finish this.
It actually was one half because y dx, because the thing goes around.
Yeah.
It's like going this way. So that's like, that's yeah. It's actually clockwise.
Yeah, it's, so the graph is calculating number for divergence number.